In this section, we'll cover using Keras for logistic regression. There's three main topics. We're going to look at a table model base class for dealing with all kinds of table form data and then putting it into a machine learning model. And then we'll build a logistic regression machine learning model and then compare that against a deep classification machine learning model. And here's the trick to remember. Logistic regression isn't actually regression at all. It's a classification technique. So when you hear people talk about regression, they're typically talking about predicting a number rather than a class. But when they're talking about logistic regression, they're talking about classifying. And we'll see how this logistic regression technique can be used to classify, along with a deep neural network learning technique to classify, and compare the two results. And now in this video, we'll take a look at the table model base class. There are several components to build up our table model. We're going to look at column and series pipelines that deal with the individual columns. We're going to look at building a scikit-learn estimator to convert all of those columns, and then we'll explore the use of scikit-learn pipelines and feature union to create an overall multidimensional array out of a table of data. Alright, let's dive in and take a look at the code. We're going to open the table model module and then zoom in Zen mode and take a look. You can see here at the beginning we're importing Keras and NumPy, and we're getting a lot of leverage out of scikit-learn, the base estimator, the transformer mix-in, and the classifier mix-in. We'll actually be using these along with the feature union and the pipeline to create our table model handling transformers. And we're going to use the scikit-learn preprocessing library with the label encoder, one-hot encoder, and min-max scaler in order to process column values to turn them into appropriate number ranges, specifically 0 to 1, so that we can use them in our machine learning models. And now we'll take a look at the extract column class, which starts off as a base estimator and a transformer because it transforms a given data frame into a single column to extract values. We save the column or series name in a member variable. There's no specific need for a fit, but the transform simply uses the data frame indexer to pick out a single column. And there's a debug wrapper here, so it's more convenient to look at when it's printed to the screen. And then let's scroll down and take a look at our first value column, the percentage column. This takes either a string or a numeric column that's a percentage and crushes it into a range from 0 to 1, like an actual decimal percentage value. The primary function in here is this thing toFloat, which turns a column of values into percentages. And it really has two cases. If the x value is a string, it strips out any percentage markers, converts to a float, divides by 100, and then finally converts it off to a NumPy float 32, which is a trick that I do for performance. Typically, when processing on a GPU, float 32 runs faster. There's no need to fit because we're just doing strict math. And on the transform, we just call the toFloat method, and then we get back in a vector of values. And now let's look at the numeric column, which starts off with a base estimator and a transformer mix-in. And this will take an entire column or series of numeric values and then use the min-max scaler to get it on the range from 0 to 1. This is actually important for numerical stability and makes the learning algorithms run quicker. This requires that we fit. We have to actually reshape the array because the standard min-max scaler understands things as two-dimensional tensors, not as simple arrays or vectors. And then we do nan to num to get rid of all the not a numbers and replace them with zeros. And then we fit it. Fitting will let it learn what the maximum and minimum values are, which serve as the divisor. And then the transform is really the same thing, except we call transform and then again cast it off as a float 32. Again, I do this for performance when I run on GPU. And now we'll move on to the categorical column, which deals with string values, such as zip codes or states or statuses, and transforms those into numbers. This is a two-part step, first with the label encoder, which will turn the strings into integers, and then a one-hot encoder, which will turn those integer values into a matrix of zeros and ones with one-hot encoding. So two steps really here. Fit actually maps to a string to deal with none values, turning them into the string none, and then we label and fit transform to turn these into encoded integer values, and then finally pass them to the fit of the encoder, reshaping again to a matrix rather than an array, which will come back with a matrix encoding values for one-hot encoding. And then the transform function is really the same thing, except rather than calling fit transform and fit, we call transform and transform, which will generate our actual output values. And again, I'm casting them off to float 32s because this is how I like to set up my matrices to work on my GPU. And here's a slight twist on the categorical column. I'm calling this the output label column. Here we're skipping the one-hot encoding step and going strictly with the numerical encoding of the labels. This is very similar to the one-hot encoding or categorical column above. It just has one less step in it. And you'll see that when we get down to the transform function on the output, we're casting these off as integers rather than floating point numbers. I'm setting up this way because occasionally it's convenient for me to build a model where my output is not one-hot encoded, but instead is numerically encoded so I can predict class labels. And now we can mix all these together. So we have the ability to deal with our three fundamental kinds of data, numerical, percentage, and categorical. And we combine these together into the table model, which you can see from the example code here how we use it. So just using the table model module that we're working on and pandas, we actually start off by creating a simple pandas data frame with several different value types. You can see percentage strings, numerical columns with integers, categorical columns with strings, and Boolean columns as another form of categorical column. And then we set up the table model mapping, which will actually transform into X's and Y's, the inputs and the outputs, and then we print those out on the screen. Using this doc test like this actually lets me unit test, but also shows you how to use the code. So now that we've got the hard work out of the way of all the column transformers, the initialization is relatively easy. We take a dictionary of transformers, an output name column, and whether or not it's verbose, and simply stash those away in member variables. And now the fit routine is where work starts to really happen. There's one peculiarity, this y equals none. That's just to have the call signature compatible with the SciKit learn pipeline in all cases, even though we're going to ignore it and focus just on the data frame because we're extracting the y's from the frame. So inside of fit, the first thing we'd look is if we already have an output member variable on our self, and if not, we start to build one. We start off by copying the transformers because we're going to be deleting a key out of it, and we start by making a two-stage pipeline, one to extract the column and one to use our transformer that is our output transformer, and we delete that from this copy of the hash we just made. And then we're going to use all of the remaining keys in the self.transformers copy to build an array of transformation pipelines. So we're going to use an array literal where we have make pipeline over extract column and transformer for every named transformer in all the transformer items. So we have a big array of pipeline values. And now that we have this array of these pipelines, we're going to stitch them together with feature union, which is another SciKit learn built in, that will take a series or list of transformations and concatenate them together end to end to build one overall giant matrix of data. And then we'll fit both of those transformers and we're set. And then finally, the transform routine is relatively simple. We just have the input and output transforms, which return a tuple that is X and Y. And then I have this property classes on the end, which is really for debug purposes. I have this here so that I can see inside my output pipeline and pull any class values off if I need to have string labels to display the output rather than just a 0 or a 1 or an integer for one-hot encoding. And that's it. This is the code. Well, that was a relatively quick tour of our table model base class.